today we will try to see the grid problems in reinforcement learning. So how the value function across iteration, how they are updated. So that particular thing we will see. We will see for two particular cases. One case is where the going right, left, up and down, the probability is same, that is 0.25. Another case is different probability is there. So both the cases we will see how these value functions across iterations, how they change. We will try to calculate them and then see. So how to calculate, you'll see. So this is the Bellman Optimality equations that we will use for calculation of the value function. So this is the reward thing, and this is the next state's v value. We use a discounting factor of 0.9 in our case, and then this is the probability. So that's the idea. So let's start doing it. So why value functions we need is, so like even in the case of when reinforcement learning, when the value function is not changing across iterations, then we say that the reinforcement learning has converged. So that's the idea. So the value function is very important. So even the actor critic case also, the actor predicts the action, the critic evaluates the action by using the value function only. So like we say that as convergence happens when the value function doesn't differ much. So like we calculate the, like we get the state, action, reward and next state. These things will capture from the environment. Like for example, if you are seeing, if you are on a road and the car is moving like this, and then it has hit the wall. For example, this is the road, this is the wall it has hit. Then in this is one episode of that particular. It has to reach some destination. Here is the destination, say for example. But in this particular episode, it didn't reach the destination, so it has hit the wall. So it might get a reward of -10. So we can sample like this particular episode. Like here we can sample, here we can sample, here we can sample, here we can sample, here we can sample. So these samples will take. Like samples are nothing but screenshots from the car. So we take the screenshot of the entire scene that you have taken. So this is the action, like he has turned right here, he has turned right here, if you see he has turned left. So steering he has, what he has here, he has the steering, he has even more left, he has turned. So that's the idea. So even if you want to, so how finely or coarsely you want to take these samples, you can even here also you can take sample here also. So what you take is these things, like see, this is the screenshot of the scene, the action that the steering action he has taken. Here he has taken right turn by some degree, like how much degree he has done. So did he get any reward? So we can put even for one step, we can put some reward like -0.04, so that he can reach the destination quickly. When we put negative reward for each step, so then then the agent feels the pressure and tries to reach the destination faster. So that also you can put for each step, if you can put a negative reward. So this is the next state, like he has reached this state, like in next state it's a screenshot will give. So that's the idea. So this is the action, the steering angle he has spent and reward he got. So these values will capture, and this we give to the actor and critic model, and then these will be trained. So actor will generate the action that he has to take. Critic will generate the v value for one for v of s case and another for v of s prime case. So then what it does is it does this thing. So it would calculate the advantage. This is what is calculated. So vs prime it got, critic it got, vs dash also it got. So gamma discounting factor and all, then the reward if he had capital it is got anything, that one, and minus this is the advantage. So the loss for critic is nothing but mean square loss. This minus this is squaring, this is mean square loss. So loss for actor is, if this advantage is positive, then that particular probability should be increased. This is the probability of taking that action. If this advantage is negative, that particular probability should be decreased. So that's the case. So this is the loss function for this, and then we back propagate and update the parameters for loss and actor. So value function is very important. So when we say that actor and critic have almost like reached a point where we can stop the training is when this value function doesn't change much. So the advantage the value function doesn't change much, so that's when we say that the actor and critic have conversed, and then we can remove the actor, and then we can make the predictions in that particular environment using the actor itself. So if the environment changes, again we have to train using the actor and critic. So that's the idea. So value functions are very important. Let's try to calculate this value function. So I have taken this toy problem. So this is a 3x3 grid. So here the reward is 1. So when you reach here, the reward is 1. So the agent will move in this. Sometimes it might circle in this only. Sometimes it can circle in this, or sometimes it will move here, like that. It can move. At one point, it might reach into this cell. Then it will get a reward. So from which states, from this state to this state, it will reach means this one will be updated. So from this state to this state, this one will be updated. So in general, how this happens, we will see if it has reached from this to this. So this is for equal probability case. So we have to do, if you see here, Bellman Optimality Equation is saying what. So probability, reward plus next state's gamma discounting factor. So that's one we will put here. So what you have to do is this one will be max of, this one would be max of 0.25 into, so the reward is 1 plus 0.9 discounting factor. The value here is 0, so into 0. So this is one thing. Next, so if he goes up, then the value is already 0 here, so discounting factor and all, nothing will come. It goes down, nothing will come. If this goes to the left, nothing will, all are zeros. So this is this. So now this one will update max of 0.25 into 1 is the reward since he went here, up event, plus 0.9 into 0. So this is the case. So since he going right, going left, going down, so all those things are 0 initially. All these values are 0. So that's why nothing will come. So max of this will be the same number. So if you see, these are the values here after iteration 1. This is 0.5. This is 0.5. Now next we will calculate for the iteration 2. So if you see here, for this one, max of, so if he goes from here to here, means then that will come to be 0.25 into 1 plus 0.9 into 0. This is this one. So if he goes up means, so he should not go up, so he has to stay in the same state. So that's the particular thing we have to put 0.25 into, so for going up there is no reward, so he has to not go up, he has to stay in the same state. So for that he has to give a discounting factor of 0.9 into 0.25. So okay, so up if he goes, this value is 0.25, right? So we can discount it and then add it to this value. So 0.25 is the probability of going up, 0.9. So this value something is there. That's why we are multiplying here 0.9 into 0.25. If it was 0, previous case, if you see here, it is goes up also. This value, previous value was 0. That's why we didn't add that particular part. So here we have to add that. So that's the thing. Next is next it can go. Next it can, if it goes up, then the same thing will come. So since the probabilities are same, this same thing, this one, the same thing will come. It goes down, then again this side, and up. So the same thing will come. So all the values will be same. So the max of this one only will come. Next we will calculate this one. This one also will be the same thing. So any direction if you go, the same value will come. That's the reason why we are not calculating in the remaining directions. So this one also is the same thing. So for this, if you see here, max of if he goes up, then 0.25 is the probability into reward is 0, discounting factor is 0.9 into the value was previous value, if you see here it was 0.25. So okay, so 0.25 is the value. So plus, so if he goes to the right, then 0.25 is the probability, and then discounting factor is 0.9, and then the value here is 0.25. Value here is 0.25, 0.25. So you get it. So if he goes in any other direction, the same value will come. Like if he goes in this direction, then again these are the only values which are there. The same expression will come. That's why I'm not putting it. So this one, if you see here, max of, so going up it is 0.25 into 0.9, 0.9 into 0.25. So no, there is no other state for this, so that's why it is only this one. If it goes this direction also, this one only will contribute, and the same value will only come, since the probabilities are all same. So that's the reason why. So if you see here, this one, if you calculate, this one will come out to be max of, so 0.25 going to the right, and then 0.9 is the discounting factor into 0.25 is the value of this particular state before this. So this one is the, so that one you put. So if even if it goes down, this one again, this one the same value will come, right? Because the probabilities are same, that's the reason why one value is one. So I have calculated these values. So next state, these will be the values, like 0.056, 0.306, or like this, these values will come. Now let's see for the case of when the probabilities are not different. So like for example here, if it goes in the intended direction, the probability is 0.8. If it goes in the opposite direction of the intended direction, it is 0.1. If it goes in the perpendicular direction to the intended direction, the probability is 0.05. So what does this mean is, if he is here, if it goes up is the intended direction, if it goes down up means probability is 0.8, and it goes down opposite direction is down 0.1, perpendicular this direction, the probability is 0.05. So let's calculate these values now. So this one is max of, so if he goes here, then the probability intended direction is this direction, right? So this is 0.8 is the probability into 1 plus 0.9 into 0 is the value here. So that's one thing. So that's the only thing. So remaining all are zeros, nothing will contribute. So this is the thing. So for this also the same value will come. So here also same value will come. So this is nothing but 0.8. So if you see here, this is the 0.8 and 0.8 are coming. And next we will calculate. This will be very interesting. Let's see this. So this 4 directions we will carefully calculate. We will calculate up, down, right, left. So put it here. So we will calculate right. So here we will put it. We will calculate up, down, right, left for everything. Okay. So from here, if the intended direction is up if he goes, so he cannot go up, so he has to stay here only. So the probability of going up, intended direction is up, so 0.8 into, so discounting factor is 0.9, the value is 0.8 is the value. Okay, so that's the thing, plus, so this that is for the upper. Then if he goes in down, there is nothing is there, goes to the right and left, nothing is there. So if he goes to the left, then it is intended direction was up, so this will be perpendicular to that. So 0.05 will come into, reward is 1, and then 0.05 reward 1 plus 0.9 into 0. So this is done now. This is one case. Now next is down. Down if he goes, then this will not contribute, down also will not contribute. So this will contribute something. Up will also contribute. Down is going, up is like opposite direction. So 0.1 into 0.9 into 0.8. So this is the down case, plus the, if he goes in the this direction, that is perpendicular, 0.05 into, I'll directly put 1 plus and all, we will not put, so it will be 0.05 only. So 1 plus 0.9 plus 0 will come out to be 0.05. So down also we have done. Now we will calculate for the right case. Right, if he goes in internal direction, then 0.8 is the probability, and then into 1 0.8 will be 1 plus 0.9 into 0, so this will be 0.8 only. So next is left case. Left case, if you, then up case also you have to put it. Up case if you put, then so that one will come out to be, this is perpendicular direction for this, 0.05 into 0.9 into 0.8. That is the case. So that's the only thing. So only two values will come here. So if you see every addition, there will be two values. Like this one was the first one plus this two. So for this also, this one was the case, this one was the second one. For this also, this one was the first, this one was the second one. Okay, for the next one is left side. If you do left side, because only two values, up and the right one only will have contribute something. So next, if he goes to left direction, nothing will come here, down also nothing will come here, up something will come, that is perpendicular to the intended direction. So 0.05 into 0.9 into 0.8 will come, plus if it goes in this direction, then it is opposite direction. So 0.1 into 0.1 into like 1 plus 0.9, so this is 0.1. So that's the idea. So if you see here, so this is one value calculation I have done. So this max of all these values, so like 4 values will be there. This is the first value, this is the second value, this is the third value, and this is the fourth value. So like that we have to calculate and then find the max of this. I think max will be this one only, will come out to be max, I think. So similarly we can find for other states also. So let's calculate for this state, because this is okay. So just calculate for this. So like the max of, I will just do for this and then stop the video now. So up if you go, then nothing is there, 0, since the value is 0 here, nothing will come. Down also nothing will come, left also nothing will come. So this direction something will come. So that is 0. So this is up is opposite perpendicular direction. So this is 0.05 into 0.9 into 0.8. So that's the thing. Next one will come. Next one is down. Down if you go, then nothing will come. This direction nothing will come. This direction nothing will come. Perpendicular direction something will come. The same thing will come. 0.05 into 0.9 into 0.8. So that's the thing. So next is right. Right if he goes, intended direction is right. So 0.8 into 0.9 into 0.8. So this is the thing. So if he right is going down, up, left, everything will be 0. So that's the thing. So right is done now. Left if he goes, so then up to down nothing will come contribute. So left side it will contribute something. So but it is in the opposite direction. So 0.1 into 0.9 into 0.8. That's the thing. So max of this, so we have calculated 1, 2, 3, 4 values. So max of this you have to take. So similarly like that we can do. So you can do the remaining calculations yourself, and you can verify that the answer will be this one. So these will be the values: 0.576, 0.836. So like that. So this is the thing. So for two iterations, so first iteration was these were the values, second iteration these were the values for the equal probability case. For the other case, when the probabilities were different, first iteration these were the values, pointed, and second iteration these were the values. So I have done only calculation for this and this, so remaining you can do it. So that's the thing. Thank you very much. This is the grid problem in reinforcement learning that I tried to explain. Thank you very much.